All right, thank you. Hi, everybody. So great to see you. Welcome. Welcome to this hybrid event, which is called the Hyperdimensional Advances in Artificial Intelligence. Very fancy. So my name is Evgeny Osipov. I'm professor at Lulu University of Technology, and here is Daswin Silva, associate professor from La Trobe University. So we two are organizing this event as part of our collaboration, which is called LTU Square, actually. I mean, because, well, funny enough, so both our universities have same acronym. So Lulu Technical University and La Trobe University. So we are both LTU. But the only difference is that LTU is located 150 kilometers below the Arctic Circle, and you are located some 3,000 kilometers from Antarctica. So that's the pretty much the whole difference. But yeah, and I don't know if we just on a rights of ice breaking. So if, in our place at LTU, we have a motto that great ideas grow better below zero. So this is a little bit questionable. I don't know. Do you have any motto here at La Trobe University?
Yeah, no.
No. Well, they grow better at any temperature, basically. Yes, right. And yes, and I will now first sketch the program, and we'll tell you why we are here and what this event is all about. And then I will proceed with the technical talk. Oops.
Can you ask online?
Yes. Can you hear me online in Zoom?
Yes, we can.
Yes. Okay, good. Yeah, so there are several goals with this event. So first of all, we will be talking about artificial intelligence. So this is, I mean, here in Melbourne, it happens during evening, so it meant to be a kind of half social event talking about artificial intelligence. And yeah, even to some degree, we will be talking about artificial general intelligence and see so what are the frontiers there. We will be talking about neural networks, and artificial neural networks. So what are the difference between them? So can we complement one type of networks with the knowledge from others, etc.? Not much, but to some extent, we will be talking about deep neural networks and deep learning. I hope that one of our presenters later on we'll talk about application of that research field or theory that I will be talking about for deep learning as well. And we will be talking about computers or computing architectures. Conventional computing architectures that we have in our telephones, in our mobile, in our computers, laptops, anywhere, appliances nowadays. Specialized computing, so computing architectures, so computers developed to efficiently execute special kind of operations, for example, to implement some cognitive functionalities or artificial intelligence functionalities. But we will be talking about an emerging technology, so which is called neuromorphic computing. So and see how AI can benefit from this type of computing architectures. More specifically, so just to narrow down the focus, the idea, so this is the first time I organized this event, at least in this format, and I pursue several goals with such event. First of all, I want to try this kind of hybrid type of event where I have some audience sitting online and the presenters being online, but also having physical presentation while, for example, during research or whatever business visit somewhere. And in this way, maybe to see how it works to make an event interactive and interesting. So talking about some advanced stuff. But also, I want to, with this event, I want to popularize a specific area of research, which is called hyperdimensional computing. Well, it's an unconventional computing technique. I bet not many of you have heard, maybe none, only some of you may heard about it. So looking at the participants here in the audience and online. But so the idea is to show why this kind of computing makes sense and how it may help in implementing machine learning or AI functionality. And as I said, so since it is unconventional computing, so one of the ideas is really not to educate you, well, to some extent, but rather to popularize it, so that when you go out of here, so you bring with you something personal or individually valuable. So what you can bring out of this event? So depending on who you are, so that can be different things. So if you're an academic, so doing research in machine learning, AI, then maybe you can learn that AI is not only about deep learning. So there are different other approaches, and deep learning also has its own limitations. So you also may learn some details, some technical details about this unconventional computing technique, and maybe apply it in your research and see whether your own field would benefit from this type of computing. And so specifically, so if you are anyways work with deep learning, so I truly hope that you still will be inspired by some of the functionalities that I will be talking about, and probably reflect this functionality and try to find applications of this technique in the scope of deep learning. So this is one of the open problems or challenges facing this research area. But then one of the ideas was to invite not only academics, like PhD students, professors doing academic research, but also invite people with more industrial background or non-academic background, so to say, practitioners, but even innovators. So I don't think we have the third class of people among the registered participants, but I mean that was would be an idea maybe for future events like this. So if you are a practitioner, meaning that you're a developer of machine learning techniques, you're working with data, you worked with data over your entire life, big data, data analytics, so you name it. So maybe you will find some useful properties of this framework that I will be talking about, and again, so reflect on your own experience and find new ways of using this technique in the scope of your problems. So I hope you will see that what I will present, this framework, which is called hyperdimensional computing. So there is another word for it, vector symbolic architectures. That it is a powerful tool in itself for representing data and working with data. So trying to find relationship between data and such. And as I said, so if we have in the audience people with at least with an interest in innovations, so maybe again, so this kind of event will broaden your horizons, and in a sense that you will hear about some new computing technology which is not out there yet. It is still in industrial research labs, but I mean, it's on the way to appear, well, sooner or later on the market, and maybe prepare yourself for new innovations. I don't know. So let's see. So that were kind of my personal intentions with such organization. And once again, thank you for coming. So let's talk about the agenda, so how this event is structured. So now it's already 5:10, and we're in the time slot for the first tech talk. I will start doing it very shortly. So I planned for 2 technical talks. So first talk is more dedicated to the to an overview of this emerging hardware, which is called neuromorphic. But I mean, in simple words, hardware that exploit principles of computations inside biological brains. And so I want to give you. I'm not a hardware person, but I want to give you this kind of high-level introduction, so that you always have it in mind when thinking about AI or machine learning. And this is important because you see now the tendency is, I mean, in the current state of the art of AI machine learning work is to focus on very, very specific kinds of algorithms and try to kind of yeah, without relation or without relating its functionality to actual challenges which are faced by this technology. And my hope is that this first technical talk will, I mean, you can reiterate every time you work with this technique and find, and probably it will bring you back to the reality, to the challenges that are facing by the current AI solutions and research. So in the technical talk 2, I will connect. So first of all, I will. I mean, by the end of the first talk, I will state some challenges of these current technologies, and so this will smoothly transition to an approach on how to deal with this this type of hardware, because I mean, well, tech talk can be perceived or listened by itself, so without any relationship to hardware, because it's. But I think it will make somewhat more sense when you kind of do relate what I will say to specifics of hardware that I will present. And then, so we will have a break, 30 minutes break. So here in Melbourne, we have some refreshments. Again, sorry that we cannot send them virtually to you in Zoom. But 7:30 p.m. Melbourne time. So we will start a second part of this event, which is demonstrations by online presenters. And I'm sorry for possible confusion. So the word demonstration, so it should be kind of taken with a pinch of salt, so to say. So the idea is that I invited 5 presenters, contributors to the area of hyperdimensional computing that produced very interesting results. Most of them, these results, they deliver state-of-the-art or better than state-of-the-art performance in their respective tasks that they solve. So this part of the event will be structured in the following way. So each of the presenters, we will have 5 of them. So there is a slight adjustment. So one of the presenters, Antonello Rosato from Italy, excused himself because of the personal reasons, and we have another talk which I asked. I asked one of the contributors to present his results, which are extremely relevant, and again, represent the state-of-the-art results in application of hyperdimensional computing to solving specific tasks. So here is the order, or well, I don't know. I think the order will be slightly different what I communicated to people, but the idea is that we will have 2 talks talking about applications of hyperdimensional computing on specific neuromorphic hardware, so for solving particular tasks. So you will hear a talk about visual spatial processing from event-based cameras. So this is interesting by itself. So again, if you haven't heard about neuromorphic computers, so it's not only about computing, but it's also about special type of sensing. So sensing that is very energy efficient. So I will tell somewhat more very, very shortly. And then we will talk about visual scene recognition in SLAM task. We will talk about distributed orchestration of workflows. Again, so I very shortly will explain how this relates to AI and machine learning. And we finally will learn about how HDC, so hyperdimensional computing, can help with the analysis of time series or signals. So each of the presenters was instructed to give a lightning talk for 10 minutes, plus minus. And after that, you are asked to join one of these breakout rooms in Zoom. So you please join yourself. So here we will have 6 different stations, and talk to our presenters. So if you have questions, I hope you have questions. So now I will start. I will continue with the technical talk, and just as a kind of a foreword. So both talks are structured in such a way that to embrace the topics to be presented in the second part somehow. Obviously, so the area of hyperdimensional computing is way broader, with lots of again cool results and notable results. But given the set of presenters, so I focused on some specific parts of the functionality. Yeah, and final words before actually I will start to kind of educate you a little bit. Where to find more information. So here I listed some papers which, in my opinion, will give you a rather complete picture of what is going on in the area of hyperdimensional computing and vector symbolic architectures. So we have 2 surveys published in ACM Surveys this year. And we have a paper in IEEE, in Proceedings of the IEEE, talking about this framework in the scope of emerging neuromorphic hardware. So that's, I think, 3 good starting points to read. Then we have a number of very good information portals. So if you want to know more, so we have a website aggregating all information about HD computing. We have regular webinar series going on every second week, every second Monday. So please visit this page for upcoming talks, and we have a mailing list of the community. So if you feel like joining, so please write a message. I will approve your membership. Yeah, and finally, so just to recapitulate that this is not just you know, a research or kind of educative talk. So if you want to play around, so there are a number of tools that you can use. Well, now I realize that I forgot to mention a whole framework for programming for neuromorphic computing, but I mean, at least as a good starting point, if you want to try different approaches in Python, so we have a library developed by our colleagues from University of California, Irvine in the US, which is called Torch HD. And I will come back to this slide again. Yes. Let us talk now about neuromorphic computers. What are those? Why do we need those? What is wrong with current computers? What is wrong with current computers, by the way? Nothing. Well, actually, they work. They work fine. They work perfectly in tasks requiring exact computations. Moreover, so talking, you know, in the context of intelligence, or biological intelligence, so the current computers, so they do way better job compared to biological brains in what matter. In what matter is performing bulky computations. So like computing, you know, complex functions. But so when talking about artificial intelligence, so and implementing cognitive tasks like classification, reasoning, well, you name it. So we can consider this, I would say, unsorted statements that I put together to understand, at least on the high level, the current limitations of the computers. So I think a couple of years ago, there was a publication estimating the CO2 footprint for different for computing different models of artificial intelligence, and the results, I think, were very notable and I would say even scary to some extent. So to train, you know, a large model in a language model, so in the domain of natural language processing, so it was estimated that it takes several days of running on a cluster of computers, and at the end it results in CO2 footprint which is equivalent to the footprint of 5 personal cars produced over the entire life cycle, basically from production through the usage until the utilization. So that's a fact. So that I mean, there are of course simpler models, so which has simpler or smaller footprint of energy and consumption or CO2 emissions. I mean, depending on how you look at it. But so this is the fact. And then on the other hand, you have biological brains, biological organisms that somehow navigate in very complex environments. So they live their life, maybe, I mean, sometimes longer, sometimes shorter, depending on the species. And they take intelligent decisions. So they learn different concepts, even honeybees. So I think people in Melbourne should be proud that this research is done here in Melbourne at RMIT by Adrian Dyer group. So they experiment with honeybees, and they demonstrated that honeybees they can master abstract concepts like above, below, left, right, smaller, larger, such thing, in just few trials. So 30 trials, so to say. So they can conduct an experiment. So bees are kind of exposed to certain visual input with different concepts, and they train them on. They attract them bees to some sweet or bitter essence, so that and depending on the shown input, and bees can select the correct route after, I think, 30 trials. So with the accuracy of 70%, which is very good for biological organisms. Yeah, but all in all, so that's not kind of an eye-opening fact, but biological brains, they need just a fraction of energy consumed by traditional computers when implementing similar cognitive tasks. So, and that brings us to the point where we need to do something about, or I mean, to begin with, we want to analyze what we want to understand. What is wrong with the current computers when they used for AI computations? And here, I think, so this slide kind of summarizes this dilemma. So the first dilemma is about power efficiency of the current architectures, current computers or microprocessors, which has stopped growing for quite some time ago. So meaning that so number of operations per joule of spent energy. So that this measure stopped growing, I guess, since 2006, and but at the same time, so we have this Moore law that tells us that the number of computational elements, like transistors, is growing exponentially. So it doubles every second year. So what's the problem here? The problem here is that the current computing architecture is tailored to do exact computations. So that when you add 2 and 2, it should be 4, because otherwise it doesn't make sense. And so when translated to the processes of happening inside microprocessors, it means that all the gates, they need to switch reliably, so between zeros and ones. And then, again, I don't want to, I will cut the corners, so to say, in this explanation, but the thing is that when you grow the number of transistors on a plate, so then you need to supply more current, so that so all the elements are kind of reliably supplied with the current, and to ensure certain reliability, so the current technology, so this so the chips are over provisioned with the energy, so they need to be supplied kind of a little bit more than needed for computation. This is on the one hand, but there is also a kind of a trade-off. So you cannot just supply more energy. So then, I mean, you end up in a situation that inside the chip, so you have some nonlinear processes, so in the electric circuits, which actually start to introduce crosstalk noise and stuff like that. So, and they start to work unreliably. So there is a sweet spot on how much energy or current you need to supply versus how fast this computational element should switch, so which is translated to the frequency of microprocessors. And and these characteristics, so the frequency versus number of elements or versus the supplied energy, so that stopped growing. So that is called power efficiency, basically. And so what happens over the past like more than 10 years, so instead, so current computers, they go towards parallelization. So we have more cores. So they work at some kind of at some saturated frequency, so which is enough for a reliable functionality. But if we want to get more computing power, so we need to get more cores, basically. Yes. So this is one thing. On the other hand, so if we look at the computer architecture, so how so processing of information is done, then we, I mean, the important aspect here is the computational bottleneck. Is to remember that there is a computational bottleneck. So that we in current computers, the processing and the memory are physically separated. And what is going on a very high level of abstraction? So all computations are done by shuffling data between microprocessor and the memory back and forth. And importantly, so the memory access is 100 to 1,000 times more energy hungry than CPUs. So that's kind of this is very important to remember. And altogether, so this creates a computational bottleneck. And so now, I mean, you can translate it to typical computations done by artificial neural networks. So you have lots of computations that needs to be computed fast. And here, so this interplay of these two factors so creates a certain limits on the overall performance. So knowing this limitation with the current computer architectures, since quite some time ago, so researchers and developers we started to look at new ways or how computer architecture should be designed in order to efficiently implement cognitive functionality. And here, so I really want to there are several possibilities in this domain, but relevant to to the topic of this evening. So I can mention two approaches. So one, which is computing in memory. So that's this approach is targets this computational bottleneck. So what if we do computations as near memory or inside memory as possible, or we kind of integrate memory inside the processing unit? Well, actually, the second approach is also falls partially in this direction. So memory-centric computer. The idea is that you keep some frequent patterns. I will tell something more about patterns soon. In memory, and you want to retrieve patterns efficiently using a set of keys. And then we have plenty of applications where this functionality is needed. And well, already here, the overall idea is that you make such a memory-centric computers in such a way that you kind of allow for certain inaccuracies. So so you kind of reduce the supplied voltage to the chip so that it becomes not very reliable in the output. So the second approach is well, I kind of took a liberty to kind of name it a computing spiking neurons. So is to look or be inspired by the way how biological brains do computing. So so this is based on observations made by neurophysiologists on how different cells in our brain or in biological brain do or perform the computations or basically react on certain stimuli. And so again, so in a few words, so in biological brains, neurons, which are special cells, so they exchange signals. So they form a kind of network, and they communicate information through pulses, so or spikes of activities. And then there are different kinds of cells, which are different by the way how they by the mechanism how they are getting excited and how they're getting relaxed in time. So again, we will not go into technical details of it, but these two types of neurons are integrate and fire. So basically, when several inputs, several pulses come in a very short time, so before the convergence to the rest state, so then the potential of the cell getting higher and higher until it reaches threshold, and then so when the threshold is reached, so this cell also sends a spike to directly connected cells. The other type of neuron is resonating fire. So here, so the excitation of a neuron, so the way how a cell emits a spike depends on the timing between arriving pulses from directly connected cells, so to say. So these are two types of models for spiking models. And so with these two models, so brain activity can be started using dynamical systems theory. So you can describe activity of a network of neurons as a dynamic system, basically. So that was about kind of inspirational part of the for new type of computing. Now I want to say a couple of words about more reflection part. I mean, what kind of computing in principle is needed for, again, for implementing cognitive functionality. And in the historical perspective, so rather long time ago, so more or less at the same time when digital computers appeared, so there was a coined concept of stochastic computing. So in the stochastic computing, so this is more or less opposite to what we have in the current computing architectures. So we allow errors. So basically, all bits of information are equally significant. So I compare it to, for example, what we have in current computers, so where we have more or less significant bits. So encoding the order of a scalar, for example. Yeah, and this type of computing is, by definition, should be robust to noise. So it means that if you have some bit errors or informational errors, still you can look at the statistics of the arriving bit stream and figure out the result. Yes, so these three principles or approaches. So in-memory computing, so this is connected to hardware. So spiking neural nets. So again, a model of functioning of brain cells. Second one, and the kind of abstract computing principle, which relies on some on statistics and not on exact computations. Some details. So now I want to link what I have said to the technology which will be presented by my colleagues in the second part of the workshop. In-memory computing. So what is existing out there? So there are, again, different approaches for manufacturing these chips. So one of the technology which you will be hearing about is called phase change memory. So it's again a relatively new kind of memory devices, in which you have a material capable of changing phase, so becoming a conductor. So depending on the supplied voltage. So you give an electricity pulse, and then from non-conductive state, so this element can turn into a conductor. And these PCM devices, these phase change memory devices, their primary usage is for non-volatile. Non-volatile as a non-volatile memory. So you store information, and it's very durable. So you can store information for, if I remember correctly, several years without kind of losing it. So which is good. However, this type of memory is not very ideal in a way that when you read out from it, so you got noisy data. So I mean, not reliable. You read in a non-reliable way. So how this technology can be used for computations, and what does it have to do with AI or machine learning? So we are talking about in-memory computation. So this PCM devices, so in addition to be used as non-volatile memory, so they have computing capabilities. So you will hear. So let me jump to the next slide. So you will hear a talk from Gitan, and who is working together with Abbas Rahimi at IBM Zurich, and they develop this technology for one-shot computation of a dot product, basically. So now, if you reflect about what I have said just now, computing a dot product is a typical operation in many machine learning algorithms. So take nearest neighbor source, take well, you name it. So with this architecture, you can do this search. You can do this computation extremely efficiently. So what you do here, in 2 words, you organize these computing elements in a structure, in a regular structure. Well, this is a 2D, but I think they're talking about 3-dimensional memories, where you store some common patterns that you observe as part of learning or pipeline in this case, columns, and then you supply a query. So not exactly same as one stored here, but similar. in the orthogonal direction, and then you measure the basically the voltage. So how so you excite these elements. So some of them become resistive, some become non-resistive. And what you see is that the closest pattern will appear as the in the output basically almost immediately. Yes, and so here is the reference to the publication where this concept, where you can read more about this concept. Yes, so that will be one of the talks in the second half. What about spiking neuromorphic hardware? Well, there are different, again, approaches to their creation. I think one of the first attempts to, or first initiatives, like large-scale initiatives to create hardware realization of spiking models was done in the scope of this human brain project. Here, I'm focusing on a specific technology which is being produced by Intel. And again, it's tailored to one of the presenters I invited to this event. And so we are talking here about a microprocessor called Loihi, and again from Intel Neuromorphic Research Lab. And again, on a very, very high level of abstraction, so so this is an attempt to implement spiking neural networks. So you remember, so this is the kind of model of activities inside biological brains inside in a silicon, so on a chip. And again, so we will not now. I do not have time to overview the details of it. So if you want to know more, so here is the reference to the article introducing this technology. But this is something emerging again. So this is a neuromorphic chip specifically designed for implementing AI functionality, and not only AI. Which is meant to be substantially more power efficient than traditional computers. And power efficiency here comes from the fact that the spiking neural networks, they exploit sparse asynchronous communication. So that's, I mean, you do not send bits of information. So you send sparse activations of neurons, and so you basically learn the dynamics of the network. So the way how to work with this technology is sketched on this slide. So or how you approach programming certain algorithm, machine learning algorithm. So first you need to, again, translate your input patterns. So whatever patterns, what are the patterns? I will precise a little bit later. But basically the data that you want to learn on, so you translate it into neural activities, so neural spikes. And then you have a mechanism for reading out patterns from the output spikes. So that's the second element. And what you do, so you implement a learning algorithm that adjusts the spiking dynamics here in the network. So you design a connectivity between these neurons, and you adjust the spiking dynamics here so that you have the desired output. So if you, for example, in the classification task. And then when you have this idea in mind on how to do these steps, then you can approach programming of the chip itself. And here I can refer to the development framework, the recent development framework, which is called Lava, in which you actually implement this algorithmic part onto the hardware. So here the reference. Some useful applications. Again, I probably don't want to spend more time on it, but they are also connected to fast retrieval of stored data. But as you will see, this is one of the, again, fundamental computational or fundamental functions in many ML approaches. So you encode, so the first publication is about implementing a k-nearest neighbor algorithm on Laihi. And the second one, so this work is about implementing so-called associative memory. So associative memory is, so if so the difference between the functional difference, so to say, between these two approaches is that here you want to know the kind of the index of the closest stored pattern to the one that you input. Here you want to retrieve the pattern itself, so the closest pattern given a key. Yes. We organized one breakout room. If you have questions regarding, how to get started with Laihi, and so if you want to learn some basics on encoding of data of different modality into Spakian representation, so then please join the breakout room, which is named Sachin Kahawala. So Sachin will be hosting this breakout room. Yes, the first speaker in the second part of this event is Alpha Renner from ETH Zurich. He will be presenting highlights on the AI functionality connected to visual odometry. So determining, he will present a solution to a problem, or at least a pitch on it, on how to determine a pose of a moving camera. Given some input scene. So if you learn, so basically the task is if you learn a map, so it's a certain displacement of the objects at some point, and then you, so if you are a robot, and then you, for example, you approach the same place, maybe from a different angle, so from a different side. So you want to kind of translate your current input to the learned one. And so that's what will be demonstrated in one of the talks. Yes. Now we are coming closer to the end of this first technical part. In summary, so what is the main message here? So we have current computers which work good, do great job in performing exact computations. They're essential for digitalization and such. So they exist for computing purposes, but also as appliances, to make our life simpler. When meta comes to implementing AI functionality, cognitive tasks like recognizing something, predicting something, classifying something, current computers are less effective so to say. And in the current state of the art, so probably it's not a surprise for you. So you either go for very powerful parallel architectures. If you want to have fast AI, for example, in self-driving cars or in cars in general, or you outsource your computations to the cloud, which is also poses a whole deal of problems connected to, amongst other, security and delays and such. So, is there a way to implement this useful AI functionality that we are, as humans, are very good at, like fast reconstruction, fast learning, learning from a few examples, on more power efficient devices, this new hardware. And this new hardware, so at least two dominating trends are in-memory computing and spiking computers, computing platforms, so to say. Which one is better than others? So this I don't want to tell. In my opinion, the truth is somewhere in the middle. So sooner or later we come to some kind of hybrid architectures, in my opinion. So where the advantages of both will be implemented. But we will have, so in the second half of this event, in the second part of this event, you will hear more about this technology from people either directly developing this technology or developing solutions running on this emerging technology. Just before letting you taking a break and switching the slides, I want to also state the challenges. So what is currently considered as a challenge with this novel hardware? First and foremost, so as I said, so this hardware exists mainly in research labs, so in industrial research labs. It means that they are kind of on the way towards production, but not yet there. So some products are more ready than others. But so in order to emerge on the market in our lives, so so this technology needs to solve several important challenges. Well, and the combination of these challenges. So they are very interrelated. First of all, they need to reduce the cost of production, and this is also connected probably to mass production of such devices. To have a mass production, so there should be a kind of killer use cases where this technology ultimately performs better than the current technology. So better, meaning faster, more accurate, spending substantially less energy than the conventional computers. And not to forget, and one of the most important challenges, again, in order to discover this killer application, so or the way to discover this killer application is to let more people to work on this with these devices, to make it kind of simpler to use. And in this case, so one of the current challenges faced by the technology is the process of software development. So how to approach programming. So far, for example, if we take the spiking type of hardware, so there is a great gap, usability gap, between for people who used to kind of conventional programming techniques. So and on this slide I kind of try to visualize what the problem is. So if you want to kind of develop an algorithm on the neuromorphic hardware, so you need really to think in terms of kind of dynamical systems. while I mean, bulk of programmers, I mean, that we educate as computer scientists, so they used to this kind of approaches. So and this transition is not very smooth, so to say. So programmers require a great deal of specialized skills to be able to work these devices. So in what follows in this second technical talk, I will present actually the unconventional computing framework, which can be used as a kind of abstraction level. So it kind of moves us closer to interacting with the with neuromorphic hardware more from the symbolic perspective, so like normal programmers would do. And we also will talk about, so what are these patterns that I mean, mythical patterns that I always talk about, but never kind of specialize. So what are these patterns that can be stored here or should be translated into neural spikes there? So that's what we will learn about in the second tech talk. Do you have any questions or comments? Did we plan for a break between the talks?
We didn't. But
Okay, we didn't. Okay, no, but
online.
Let's get.
Probably their first research workshop where the food remains untouched. So,
so let's check the remote participants. So no questions there. But a message to remote participants: please feel free to unmute yourself and interact even during the talk. So I mean that wasn't meant to be very formal, so to say from the beginning. Maybe take a cup glass of water. So a message to online participants. Maybe we take 2 minutes, 2 minutes, 2 minutes leg stretching break. I don't mean that. How are you?
I had a event yesterday after.
Yeah. How did it go?
They also have pizza coming at 7. Hang around for that. It's really good pizza from like New York style pizza. Yeah,
wow.
On Flinders Lane, probably. That's why we're yeah.
Yeah.
We have 31.
Yeah.
What's good?
Huh?
We have 31.
Yeah.
Including here. 17.
Okay. Please.
It's in person. Yeah. Yeah. You're going to join online. The big one. Yeah, one's like a meeting. We can join online. Okay. But we'll be on campus. Both will be in 301. Yeah. The large. Just like what
So, guys, what do you think? So, shall we continue? So, take your food. So, take all food that you have, and so please take some refreshments with you, so we can continue.
Yeah.
So, welcome back. That wasn't a very long break. Yeah, so now we will continue with something softer, so to say. So we will talk about this framework or a research field or area which is called hyperdimensional computing. And I named this presentation a hyperdimensional path to artificial general intelligence. Sounds very fancy. But again, so I mean, every time I present this topic, I'm trying to add some maybe new angle to the presentation and see which one works better with the audience. And I just want to make a remark that that what I'm presenting, well, by the virtue of this event or this agenda, it is connected to the hardware that this emerging hardware that I have presented previously. But so this this framework can be considered without relation to specific hardware. So this is just a computing framework. So so you a kind of interesting, not very usual way of computing. So manipulating data in this sense. Before continuing, or before actually introducing this hyperdimensional computing, or another term is vector symbolic architectures, I want to give you a kind of a bootcamp class about selected aspects or selected definitions about artificial general intelligence. And I named this part like Intro to AGI in 3 slides. But again, just as a recapitulation, I know that you all know that. So if we talk about an intelligent agent, so it is system that a system. So if you talk about biological intelligent agent, then it's a biological system functioning in some environment, like me staying here, so interfacing you, and presenting these slides, organizing this event. And while doing that, or in order to be able to do that, so I internally I have certain ideas about what is going on. So I know how to define you in the audience. I'm aware about myself. I know who I am. And so, in other words, I have a kind of very complicated complicated model of this environment, of this reality. So, or in terms of artificial intelligence, of this world. So, it's a situational world that I'm, of this world where I'm situated now. And this model, it helps me in performing different cognitive actions. So I can recognize that I mean, there are some humans sitting here, some ladies, some guys. So now I'm doing analysis, so I can say that I mean, we have maybe 1% of, so it's not very gender balanced audience. So I can do prediction. Maybe next time it will be better. I don't know. So and maybe it will be better if I will tell Daswin a little bit longer time in advance this task of attracting people. And the reaction. So we, I don't know. So you may, I mean, each and every of us react different on different inputs and stimuli. But I mean, so here we are, intelligent agents with all these complex behaviors. And but now, if we want to, so we are now moving closer to adding this artificial part to it. So, but before doing that, so we want to probably define, so what or kind of formalize what the world model is, or actually what the model of the world models of the world are, since basically I may have, or I do have, a different model for example, doing some tasks in cognitive tasks about humans. I have different model about furniture, about situations, about relation, etc., etc. So in general, a model includes models of attributes, objects, relations between those. Attributes again. So now we are talking about some machine learning stuff. So features, like characterizing a certain object. Objects can be of different type as well. So real objects, unreal, abstract objects, and etc. But and then relationships. So everything is kind of interrelated, and if you start to analyze. Well, if you want to describe a certain situation, so it can be described via spatial, temporal, part, whole relationships, etc. So again, so this is on the level of definition. So that's again, we started from the definition of what intelligence is, and so going through the necessity to have a model describing this thing, and then so what model should consist is description of somehow description of attributes, objects, etc., and the relationship between them. So that's it. And then also, so the last slide again, so which is relevant to the context of this talk, is a specific type of relationship between objects or attributes, which is fundamental to many objects and situations. So this is part whole hierarchy, so which is exemplified here. So well, here it is exemplified by a car, but I mean, you can take, for example, a chair, so as a as a model which contains of some subparts like wheels, amongst others, and wheel can also have parts, etc., etc. So that's thing. But I mean, this relationship part whole. So it also exists, or you can meet in different other situations, like for example. Describing proteins, describing chemical substances, language itself. So all complex objects can be viewed with the help of, or described with the help of this type of hierarchy. So I presented all this story for two purposes. So now I will come to the domain of defining the I mean, what is missing? I mean, what is the current challenge of artificial intelligence? But also showing that, I mean, one of the presentations or one of the presenters that I asked to be here today will talk about representing workflows. So tasks to be distributed to different objects in a kind of distributed environment, like wireless environment. And so again, one can ask a question. So how does this relate to the artificial intelligence? So and here is basically the answer. So I mean, this task by itself. Can be viewed as part of the cognitive tasks of an intelligent agent. But so now equipped with these definitions, so let us have a look on what is going on in the area of artificial intelligence. So what is, I mean, when we try to implement all this intelligent functionality in computers. And here, so we have two approaches, or two camps of academics and practitioners that develop different sides of this intelligent behavior. And these two approaches are called symbolic AI and neural networks, artificial neural networks, or in AI terms, connectionist AI. So symbolic artificial intelligence, which is also called good old-fashioned AI, it relies on the logic to model knowledge. So you what you do? So you kind of handcraft symbols and rules. You define and you have a language to represent these rules, and you actually define rules of inference, so to implement a certain logic. So artificial neural networks, on the other hand, tries to model a knowledge or learn this knowledge by imitating representations of the brain. So basically, the deep learning stuff is in here. So we want to kind of observing kind of raw inputs, want to deduce what kind of categories we deal with. So, for example, in classification tasks. And so the strong argument of this approach is that you're kind of directly interacting with the environment. So you are so whatever categories that you, or whatever knowledge that you discover here has direct connection to the actual phenomena, physical phenomena that you're dealing with. And this is this is called symbol grounding problem. And so you're probably also aware that still one of the unresolved disputes in the area of AI is so which of the function, which of the approaches is the right one. Well, actually, maybe I formulated it incorrectly. Rather, so the dispute is to find an approach that embraces both, so the strength of both approaches. So interface in the physical phenomena, in observed phenomena, and being able to deal with this knowledge, like this symbol, in a symbol-like manner. So what does it mean? Relate symbol-like entities. So when you observe something, so the main question, so we can translate this this challenge is to a problem whether we can take abstract objects. So can we take abstract objects like features, events, scenes. These objects, these entities can be of different modalities, so a picture, audio signal, tactile input language, and represented in a neural network compatible way. So so that we can bridge these two approaches. So I introduced this challenge by stating so whether we can represent the symbols so that they are compatible, but I mean it works in the other way as well. So can we interpret the results obtained here and use it in symbolic computations? And actually, so all these objects can be described with apparently few data types in computer science. So we don't. So what we need well, we need maybe vectors. We need sequences, graphs, and a few other data types in order to be able to well, describe different complex situations and world models. So, and as such, so that's what I'm presenting. So today, so which is called vector symbolic architectures. So this framework, computational framework, is meant to be a bridge, so of this kind. So in a way that so the vector part in this term corresponds to, I mean, should have, or you can see it as a foot into the connectionist approach. So it can be interpreted as neural activation somehow. At the same time, so you can treat these neural activations as symbols, and you want to have a possibility to combine the symbols to describe different situations, or well, at least through data structures, some standard data structures. Yes. And so the starting point, again, so the starting point, again, was an observation by a neurophysiologist that activities in the brain, in biological brain, are high dimensional. So any single stimuli or any stimuli to stimulus to a brain activates many neurons, like hundreds neurons or thousands of neurons. And so just kind of being inspired, so now it's an inspirational part, so of this observation, can we create such a computational framework where all concepts, variables, attributes can be presented by high-dimensional patterns somehow. And so that was kind of one of the starting works done by Pentic and Erva back in the end of 1980s. But then I want to continue with this kind of observation. Then somewhat short time after that, so we can, so this observation is not complete without saying that activations in biological brains are sparse. So I mean, we have like billions of neurons, neural cells in the brain, but at any single time, so it's only a very small fraction, like tiny fraction of them are active. So, so just to complement again the inspiration, so why don't we create such a computational framework that in which concepts, variables, attributes are represented as random, high-dimensional, and sparse vectors? So. And so these type of computations were proposed and developed by Dmitry Rachkovsky, who is actually online today as well. And then, so the hyperdimensional computing or vector symbolic architectures, and we have yet another pioneer here, but I didn't find a good picture of you. So, so Ross Geller is sitting here in the audience.
Live.
Yeah, so we have live, exactly. So we have a live picture of him. So now we are talking about so how we can use these representations to so if we represent everything, like all data structures as high-dimensional vectors, so how to represent complex data structures. So, and all these frameworks that I have described and the one that Ross suggested pretty much at the same time. So it introduces algebra over vectors. So you have vectors that describe certain concepts, and then you have some algebraic operations. And so you do computations, well, compared to the conventional computing approach, so where you do computing on numbers, here you do computing on vectors only. As a whole. And then you need to have, I mean, one essential requirement is that you need to have an access to many vectors. So because you are about to create a system capable of symbolic operations, and one of the requirements of being a symbol is that, I mean, you can create a symbol on demand, basically. So to symbolize something. So I mean, you need to have an access to infinite number of, or pretty much infinite number of symbols. So how can we do that? Well, here is a boring slide with with essentials of hyperdimensional computing. So, and the idea is pretty much simple. First, you decide on a numerical system that you want to operate in. So, what do I mean by this? So, what numerical systems are there? So, we can use integer numbers, real numbers for computation. We can use complex numbers. And we can, well, we can be also even binary, so they're just zeros and ones. Well, there are plenty of numerical systems, but so we need to choose one of them. And then, so we will somehow transform these attributes, so everything that we need to describe a world model or a world model or a phenomenon, we will somehow assign a symbol, which is a vector in this numerical system. And the important point is that so the dimensionality, so the number of elements in this vector should be high. So in order of, well, depending on the system, maybe from it varies from 100 to hundreds of thousands of vectors. So, and that this vector, so you immediately should kind of, to me, it helps anyways. So when you hear vector, so you probably can imagine, or you can translate it to possible neural activity. So this is some pattern of activation of neurons. And yeah. And if you want to create a symbol, so remember, so what is the property of a symbol? Symbol is is something that uniquely name something. So the symbolize something. So and two symbols, they are kind of different initially, unless we explicitly tell that two symbols bear certain similarity. Or so take symbols, say A and B. I mean, that's letters by themselves, so they look differently. But I mean, then as a result of you know, putting them in the framework of the alphabet, so then you can say that and saying that B follows after A, so then you can say, okay, these two symbols are kind of related or nearby. So to generate symbols, so the atomic symbols, so we will generate vectors randomly. So and that's pretty much works as I mean, delivers this functionality. So you take a vector of this dimensionality and randomly choose the values on each position from certain distribution. And probably again, so I will not say, normally I have a slide with referring to certain mathematical framework. I deliberately remove it from this presentation, but there is a meaning of having vectors of large dimensionality, so like several hundreds or several thousands. And this is connected to the property of randomness. Or to the property of dissimilarity of resulting vectors. So the intuition is very simple. So you take a very short vector, say 3-dimensional, so x, y, z, right? And say that you have zeros and ones only as components. And you randomly select either 0 or 1 in each position. So what is the chance that you will generate same vector, so to say? So it's very high. So eventually, so yeah, I mean, if you want to create a new symbol, first of all, you don't have too many possibilities with 3 dimensions. But the more dimensions you go, so the larger number of items you can encode in them. And so again, I can refer to I mean, to give you a sense of numbers. For example, you know, IP addresses that are given to each and every computer. So they are 32 bits. 32 bits. It means that we, in total, we can encode 2 to the power of 32, like 4 billion combinations, right? 4 billion combinations, 4 gigabytes. Actually, again, referring to the internet, so, the new, the current version of the protocol, it uses 128 bit addresses. And the number of combinations you can encode is 2 to the power of 128. And the number, this number is hard to imagine. So it actually corresponds to or relates to the total number of atoms in the observable universe. So 2 to the power of 128. So it's a lot. So the more you go, the larger is your representation space. So the more dimensions you take, the larger is the representation space. And in this large representation space, so again, so this is the intuition. So you pick kind of one number at random. So with a very large probability, so it will be kind of very far away from the next number that you pick. But again, so there is a proper mathematical theory that gives more formal explanation to this phenomenon. But for us, it's important. So we stick to some dimensionality, large dimensionality, and if we want to generate a vector that would that would have certain meaning, so in other words, symbol, we just randomly generate them. But then what we want to do, so now we are talking about architectures. So we want to do something with the symbols. We want to manipulate with them. And we will do it by means of these four algebraic operations. So they have, actually, if you forget the text here on the right side, they are just summation, multiplication, inverse to multiplication, and a permutation. But in this computing framework, so these operations, they are also given certain meaning, some again, which is easy, which is intuitively understandable. So this plus operation is referred as superposition. So if you have a number of symbols, so this A and B are now these big vectors, randomly generated. So when you add them together, so you kind of, and remember, so here, all these operations, they preserve the dimensionality. So this addition is without carry-on operation. So you always do the bitwise or position-wise operations, and you never go beyond this dimensionality. So this is your dimensionality of the system. So basically, when you add these different vectors, you get one vector that contains, which actually denotes all of them together. And now it's, I mean, kind of tricky to apart. When I say that, so those of you who didn't work with VSA may wonder how this is possible. And this is possible, or it becomes way more clear if you add some extra mathematical components to it. So you need to add a measure to the system. So you need to somehow assess the quality of your constructs. So you introduce a measure and a measure of similarity between your vectors. And again, so I will not go into the math part of it, but so there are different ways to. So this measure of similarity in the vector space. So you can think of a measure of proximity of vectors. And what is it? I mean, you can imagine our Euclidean two-dimensional space or three-dimensional space, and vectors are these arrows. You know, you remember from school. So a measure of similarity between vectors is, I mean, you can relate two vectors by the angle between them. So if they start from the origin, so you can have orthogonal vectors, or you can have collinear vectors, for example. So the closer they are, so smaller angle is, so the more similar they are, kind of, obviously. And then in this case, so there is a mathematical expression for it. So you don't take the angle as a measure, but you take a cosine of this angle as a measure of similarity, basically. So, and again, referring to your skills in trigonometry, so cosine of 0 degrees is what? Huh? What? 1. Yes. And cosine of 90 degrees is 0, right? So when the vectors are orthogonal. So that will be our measure. So if you take this in addition to the fact that these vectors are random, then the result of this operation will be similar to each and every vector that you superimpose, you add together. So this measure will be different if you would multiply them together. So, but again, so that's maybe less important at the moment. What is important in combination with these properties with respect to the chosen measure of similarity between them, you can start. So I will skip this slide. You can start actually creating or architecting your data structures. And then it is here when it comes to very interesting stuff. So, so here you see the different equations, and so the way how they encode, the way how they encode different data structures. For example, so if your object is has a tree structure. So how can you approach encoding them? So you first of all, so you need to define a symbol of an object being on the left or to the right of it. And so this is a symbol. So and symbol is a vector. So you just generate them at random. So two vectors at random, left, right. So L and R. And then, so you want to encode an object. So this, depending on the task, so it can be, I don't know, maybe a notion of a chair, and the notion of on the left, and the notion of a human on the right. So, for example. So you put a symbol for this object on the left, and you encode it through multiplication. And then you can do the same for the right part. And then you can even create nested structures. I will not go into details of this computation. So all this information exists in the papers that I refer to. And then if you are interested, I can clarify later on. But in this way, we have a way to actually describe non-trivial data structures. And what is important in all these cases is this result. So the result is just one vector. So an entire tree or an entire graph or an entire table can be encoded in a single vector, which again, so immediately when I say vector, so you maybe you may refer to some neural activations immediately. And then basically what you need to do, you need to have a way to actually produce encodings for these objects, different objects from the environment, that from your world that you want to model. You want to come up with the symbols. I mean, what is A? What is B? What is C? I told you that some atomic symbols, they created at random. But then remember the discussion that we have this complex, I mean, we have complex, all objects are complex. So this part whole hierarchy. So and basically pretty much all phenomena that you deal with, take a picture, so like your favorite MNIST data set, take speech. So when you speak, so this audio signal, take text. So they, I mean, they're complex objects, and you need to find a way to transform them into to this vector representations or hypervectors. Yes, and there are actually interesting. Well, there are different ways you can do it. So many of the approaches are known. New approaches are being developed. Approaches based on deep learning networks also is there. So taking the representations from neural layers and using them in this context as hypervectors. So they also exist and such. And by the way, so one of the presenters who is already online, so Kenny Schläger from Technical University of Chemnitz in Germany, he will talk about how to use this framework to represent time series or signals. Yes. Let me see. I probably need to speed up a little bit. So here is another example. So now related to encoding of texts. So there are different tasks you can do, or machine learning tasks you can do with text. One of them could be, for example, language classification. And again, so one of the ways to solve this task is to observe the statistics of combinations of letters. So we are talking about written texts. And different languages, they have different combinations, so different statistics on of appearances. Of different combinations. So the traditional way of doing collecting the statistics, if you, I mean, it's again easy to understand. So you have your atomic alphabet, so say some 27 letters, Latin letters, and a white space, and then you enumerate all the possible combinations. So, for example, combinations of 3 letters, so which are called trigrams. So you enumerate them, and then so how many combinations you have is 27 to the power of 3, right? So so all possible combinations. So it's like, what is it, 700 something. Yeah, and then you scan your text. So with a window of 3, and simply do count the number of appearances. So you collect the statistics, and then you learn the model. So if you have some ground truth, like this text is English or German, so then you can train a model that that will take a new text, collect the statistics, and tell, okay, here you go. So I guess if you listen to me carefully, so in this classical way of describing statistics, so this number of combinations that you need to kind of maintain, it grows with the size of this window. So the larger this window, so the number of possible combinations is exponentially increasing, right? And then, so basically, at some point, it becomes really unbearable to keep all this data structure. So with hyperdimensional computing, and that is, again, so at least this is a message to practitioners. I mean, you can use this approach for kind of very compact data representations of such classical data structures. So in a kind of, you can think of it as a data compression, so to say. So you would do it by generating random vectors for the letters of the alphabet, and then on the fly constructing, encoding the combinations of 3 letters. So, well, again, using this approach, and then summing them up. So, and then at the end, you will get a single vector that contains all possible combinations of n letters. Another example, I probably skip this one, so that it will take longer time to talk about. But maybe of a similar, another application of a similar kind of encoding or data representation. So this is something we did together with Lothrop team. Sorry. So we analyze traffic patterns in the Greater Melbourne region. So the data here was a recording of car passages through intersections, right? So basically, the database consisted like so intersection identity, so the time when the car passes, and the Bluetooth address, address of a Bluetooth device in the car. And then obviously some cars, so they passed. I mean, they moved. I mean, according to their own free will, so to say. And and the task is to see whether there are patterns over a certain period of time. And so how to, so this is challenging. So you know that some cars pass like 2 intersections, some go through 5 intersections. So how to represent this data? So we used a pretty much similar approach to get input data of a fixed dimensionality. And when you have fixed dimensionality input pattern, so now we talk about a vector pattern that describes a trajectory. So a car moving from here to here to here. So number of intersections. And then we simply, based on the similarity between these patterns, we can say that, okay, so this and that car, so they have in common, for example, this stretch of the road, for example. But the important point is that this analysis is possible in a more efficient way with this compact data representation. I think yes. Yet another, so now I'm connecting to the last of the invited speakers. Very interesting work where hyperdimensional computing and vector symbolic architectures are used in real applications. In this case, we are talking about visual scene recognition for simultaneous localization and mapping. So the idea is that you have a robot. So you have, well, in this case, we have a visual stream, like a camera. So maybe so you have visual streams in different weather conditions, in different time of the day, and then you place a robot somewhere in some new place, and it should figure out and all this of course the stream is annotated, so it's given coordinates on the map. So the task here is to understand, so given a scene, understand where you are in the map. So, and it means that you need to take the description of a scene and do very efficient or very fast search for through a huge database in order to accurately determine your current position. And here, so again, so I will not spoil much, but HDC VSA representations can be used to create a single representation for many possible descriptors. And in this way, you achieve both higher accuracy of detection of the place, and also increase the speed of the lookup. So once again, I want to show this slide. If you're interested to learn more or to play with this framework, computational framework, so I can refer you to this Torch HD library in Python for Python, which facilitates your entry into the hyperdimensional worlds. And once again, if you want to know more, so here are two useful resources to remember. So the site sgcomputing.com and our webinars with already 3 years of recordings on different topics. And that concludes my other talk. So, and I thank you for attention. So thank you. So what's happening now? So I want to ask people in Zoom also to unmute yourself and maybe be with us and participate. So according to the agenda, we have half an hour break. Well, of course, feel free to disconnect and join us back. But if you want to participate in discussion, so you are on loudspeakers here. And so feel free. Or type your questions in the chat. And by the way, so Sachin, did you start this breakout room on Laihi? Yeah. So you may also consider joining the this breakout room and ask about Laihi hardware. So the spiking or talk about it. So in the meantime, but otherwise, so we resume this event in half an hour. So with the online presenters. So in the, yes, in a global context. So I try to put your topics in the global context of AI implemented using HDC VSA, also connected to neuromorphic hardware whenever possible. So now, what I instructed you to do is to prepare a lightning talk for up to 10 minutes. And after that, we created a number of breakout rooms. So here you go. Let me see. I will show you just to be on the safe side. Yeah, here are breakout rooms. So the audience join these rooms themselves. Why don't they see?
See this one.
Huh?
The slide.
No, but because of that. Do they see it now? No.
No.
Yeah, well, nevertheless.
Now they do. They do.
No.
I think it's sharing the whole screen.
No, they don't.
Listen.
Yes, okay, so yes, please. Yeah, if you can scroll down, Sachin. So we have 6 breakout rooms. So one for each speaker. After the presentations, please join these rooms and ask questions. And here in the audience, we also will do so. All right. So now, without any further delay, so I leave the floor to Alpha Rena. So please, Alpha.
Hi. Yeah, let me share my screen. Can you see the slides?
Yes.
Now?
Yes.
Okay, great. Yeah, my name is Alpha Renner. I'm a postdoc at the Institute of Neuroinformatics in Zurich. Hello to Australia and everywhere else in the world. Thanks a lot for inviting me. So since you already heard, if I understand correctly, a 1-hour intro on neuromorphic hardware, I'm not really gonna introduce this properly now, but just let me motivate quickly why we use it. So the idea of neuromorphic engineering is to build computing hardware that mimics the biological nervous system. Why do we do that? On the one hand, the brain only uses 20 watts of power for all the amazing things it can do. And also, nature has done other very interesting, amazing things. Like, for instance, the fruit fly only uses 200,000 neurons for all these very complex behaviors that it shows. The most important features of neuromorphic hardware that is shared among almost all the hardwares that exist is massive parallelism, in-memory compute, local learning, and event-based asynchronous processing. So the problem, however, with all these features is that it's very different from the conventional processor architecture, which means that we cannot just run algorithms on neuromorphic hardware as we are used to. So, and that is one of the reasons why we try to use VSA to actually link the functionality that we want to the hardware level on the lower level. Why is this still neuromorphic? I think also the brain actually likely uses some form of abstraction. For instance, the cortex, right? It's built from a lot of similar looking elements like cortical columns, or also called the cortical canonical microcircuits. So the two projects that I want to present you today is, on the one hand, so they're both based on a network called the Resonator, which you can see here. One of the projects is disentangling such an image into its components. On the one hand, into the different letters, but also it tries to understand what letter we have here, what color it is, and where it is located. This is it goes beyond simple classification that neural networks usually do. And the other task that I'm gonna present you is called visual odometry. So we estimate the camera motion and we form a map of the environment based on the visual input that comes into the camera. So yeah. The VSA that we are using, and I hope you already heard of it in the previous talks, is Fourier holographic reduced representations, and the vector that is the basis of this kind of encoding is a complex vector. And a complex vector, in our case, if you discard the amplitudes, it's basically a vector of phases. So the way we actually implement this in the hardware, or how we, at least we don't always implement it. So in most of the cases that I'm going to show you, it's actually just a simulation, but I'm also going to show you in the end one implementation on the hardware. And there we have actually, per phaser, we have a single neuron that spikes periodically with a specific phase relative to a global window, which could, for instance, be something like a theta wave that we also see in the brain. So this is how we implement phasers in spiking neuromorphic hardware. The binding operation, as you might have also heard, is in Fourier holographic reduced representation, it's just a phase shift. So we have one vector and another vector, and in an element-wise manner, we add this phase to this phase and get out this phase in the bound vector. So now let me quickly motivate why we use VSA to represent scenes in the first place. So just imagine a very simple visual scene with just, let's say, the letter A, okay? So in a neural system, what could we do to represent such a scene? We could just have a neuron that stands for color and another neuron that stands for another color, right? And just neurons for all the colors. And we could have neurons for all the letters. And now this scene would be represented by having the red neuron firing and the A neuron firing. This works as long as we have just a single object, right? Now we have also a C, and then we would have the blue neuron firing and the C neuron firing. But now we no longer, actually, if we just get this as a state, we no longer know if the C is red or the C is blue. And this is commonly called the binding problem. So what we would have to do in order to represent such a scene would actually to write a combinatorial space where each neuron here corresponds to a combination of two features. And then we can have the red A neuron and the blue C neuron. But we would also have to have a green C neuron, a yellow C neuron, and a red C neuron. So this, of course, is not really efficient, since we could also have other features like texture, font size, location, rotation of the letters. If just every of these features that I just told you has, let's say, about 40 values, we would already need, just to represent the entire combinatorial space, we would already need 10 to 11 neurons, which is as many as we have in the entire human brain. So that's why each of these locations in this combinatorial space, instead of having a neuron that represents it, it could also actually be represented by an activity pattern, which basically means by a VSA vector. So that's what we do. We represent each of these locations, for instance, the blue C, as a VSA vector. That is a bound vector out of the color vector and the letter vector. And for this, we use a sequential binding. So in this case, since it's the fourth color and the third letter, we just bind 4 times C and 3 times L. And that's then one single vector that points to this location, kind of. And the way to move through this space is just here in this combinatorial representation. It's just a jump from one location to the next in the letter direction. And in the VSA, this is just a binding, in this case with the letter vector, in order to get from C to the 4, L to the 3, to C to the 4, L to the 4. Okay, so this is how we jump from here to this location, to the blue D in this case. So now let's go to our actual task that we're trying to solve here. So let's say we have this blue C here in our scene. The sensory system encodes this into some neural representation that is high dimensional and distributed and corresponds to this L to the 3, C to the 4. So creating such a vector is actually really easy if we know we have a blue C, right? However, going back from this high dimensional representation, from this VSA vector, into the low dimensional understanding of there is a C and a blue, a C that is blue, it's actually a very complex task, because what we would have to do is we would have to calculate the similarity of all possible letter color combinations in order to see, it actually has a very high similarity with L to the 3, C to the 4, which is the blue C. But doing that, of course, would completely render like obsolete using VSA in the first place, because then again we have to get this super high dimensional representation and combinatorial representation that we wanted to avoid in the first place. So the resonator is the way to avoid this, because the resonator, what it does is it actually takes out each of the features that are bound together in this distributed representation. It takes them out of the input separately, instead of doing a decoding in one go. It iteratively just estimates all the different aspects that are encoded into the VSA vector. In this case, it's color pattern, the vertical and the horizontal shift. So how does this work? I think in 10 minutes talk, I cannot give you the perfect intuition, but just imagine that the input is basically like bound together the letter vector, the horizontal shift, the vertical shift, and the color. So now each of these boxes kind of unbinds all the others. So the age box unbinds the current estimate of V, the current estimate of D, and the current estimate of C. And what remains would be H, which is the horizontal shift, and so on. And doing that iteratively actually leads to one correct solution in the end that is an attractor of the recurrent dynamics of the system. And if you reconstruct the result here, it would be exactly what you get in the input, but you know now that this is actually a letter X that is shifted by a certain amount and has the color cyan here. So here we are looking at the dynamics of this resonator over time. So you see here, so these are iterations, and this is the low dimensional like meaning that the VSA vector encodes. So at the beginning, you see it's very confused. It does not actually know anything about the input, but over time, here it's roughly 15 iterations. It starts getting the correct solution. And you see at first it's actually a superposition, so a bundled VSA vector of all the different variants that it tries out in parallel. That's how it can solve this task that would usually take hundreds of thousands of comparisons in just 15 iterations. So that's then applied several times. So we take out the X out of the equation, kind of, and then it also focuses on the other letters. This is another hierarchy of iterations here that we introduced for the letters. So now you might ask, what about rotations? Rotations are actually included here by doing the log polar transform, because in the log polar space, a shift corresponds to a rotation and a scaling. So we can apply the log polar transform to a VSA vector, and in the VSA space, go into a different encoding, and then the binding operation actually becomes equivariant here with rotation and scaling. That's how we can do these two dimensions also. So the actual resonator that solves this then is actually a two-compartment architecture that in the one compartment solves the Cartesian, and in the other one the log polar space. So I'm not gonna do the recap because I'm kind of already running out of time. So how do we do the visual odometry? It's very similar to what I just showed you, just that we ignore colors and we don't have separate letters, but all we need to find is now the mapping of two images together. So for that, we create this larger architecture that first takes in input from an event-based camera here. So now everything is dynamic. We encode this over time. The hierarchical resonator that I just showed you takes out the X and the Y shift and the roll rotation. And whatever we get there is then transformed and added to a map that we form while the camera is moving over the input. So I'm not sure if you've heard of event-based camera, if they were already introduced, but fundamentally it's a camera that only sends events instead of frames. It sends events whenever something interesting happens, something changes in the image instead of sending a frame like a normal camera. Yeah, so this is the result of this resonator process. So here I'm transforming the map into the input space just to visualize how well it actually works. So I'm taking whatever the network thinks is there and rotate it into the input space. And you can see that whenever the input moves out of the view, the map still expects the objects to be at this location, right? Okay, so it also works for longer simulations. So as you can see here, the orange one is our network and the blue one is the ground truth. So, and we have the roll, tilt, and pan of the camera here that I'm showing you, compared to the inertial measurement that drifts very strongly, right? Okay, we also outperform deep network architectures, although there are not many that actually tackled this specific task. Yeah, so I think since I'm running out of time, I'm not going to show you. Well, I can quickly show you this video still. Is it fine? So this is now showing the same thing with a map, and this is the green one is the event-based input. And now what we are doing, we take out this bowl here out of the image. In a few seconds, someone will get it and take it out, and you will see that the red map is then slowly adapting to the new input, which means it actually decays out of the map. So the map dynamically updates to changes in the environment. And this is actually just done by a VSA bundling operation. So we always bundle onto the map the newest input. So over time, of course, it will adjust to what's currently out there. Okay, so I implemented this on the Loihi neuromorphic chip. I think I don't have actual time to.
Yeah, I think we can proceed. So if there will be questions, so we can proceed in the breakout room.
Yeah.
Probably.
Let me just tell you that this is like 350 times more energy efficient than the CPU implementation. Yeah, thanks a lot for coming. And thanks to my collaborators and students and so on.
Thank you, Alpha. Thank you very much. So I applause from here and online speaker, audience. So you please feel free to stay here if you don't want to be alone in the breakout room. So we now continue with the next speaker.
Hello, I hope you can hear me.
Yes, and now I also yes, hello Per, and I wasn't sure about your new affiliation, so I put your old one. So I'm sorry for that.
No problem. So very recently moved from Chemnitz to Koblenz. Now I'm their professor in Koblenz. And the work that I'm going to present today is mostly done in cooperation with the University in Chemnitz. So I'm going to talk about VSA HDC-based image descriptors for image retrieval and localization. So what does this mean? So I'm working in the context of mobile robotics. So we have robots like these that you can see here, and they operate in unstructured terrain and they explore new terrain, unknown terrain. And one very important task is to create a map, an internal representation of this unseen terrain, and also localize within this created map. So one very important subtask is to recognize already seen places based on camera images. And I will talk about an VSA HDC approach that solves this task. Okay, first I want to give some intuition in this visual place recognition problem. So basically, it's just the question, which place from the database is shown in the query image? So on the left, we have an actual query image, the current image from the camera. And we also have a database of known places, illustrated by this video on the right side. Now the question is simply, which frame from the database, from the video on the right, corresponds to this query image? And this is rather simple under those conditions. And our current research question is, what if we have changing conditions? So what if the appearance of the environment considerably changes between what we have seen during creating the map and when we later come back? So this is a typical scenario if we have a robot that operates over a long period of time. For example, autonomous cars. Okay, so this is a basic image retrieval problem, but if we put this in the context of mobile robotics, we have a lot of additional knowledge, a lot of additional structure in the problem. So for example, the camera will not arbitrarily jump between different places in the world. And in general, we think that VSAs and HDC are a very, very powerful and promising approach to introduce and integrate this additional structure and knowledge of the problem into existing solutions. And I will talk about this briefly in the next few minutes. So if we look into this problem, we basically just ask this question, given the Kahawala query image and the first database image. So is this the same place? Do these two images show the same place? And then we repeat this question for all other database images. And we repeat this question for all further query images. So we have a lot of questions we want to answer. So typically we have like thousands of images in the database and thousands of images in the query. So let's have a look what we try to do to answer one of those questions. So we want to compare this database image to that query image. And the way we do this is by means of descriptors. So a descriptor is one or multiple numerical vectors extracted from images that have high similarity for images of the same place and low similarity for images of different places. And this is the connection to, or direct connection to VSA and HTC, because here we suddenly have those high-dimensional numerical vectors that describe the images. As I said before, we have thousands of images in the database and in the query. So whether this whole task is feasible or not simply depends on the required computational effort for each of those image comparisons. And we have basically two techniques. So the first case is a holistic descriptor, just the idea that I already presented. So we have one descriptor vector for the database and another numerical vector that describes the query image. And in an example where we have 2,000 images in the database and 2,000 images in the query and 4,096 dimensional descriptors, we have about 4 million comparisons. This is really a lot already, but the runtime on my laptop is still half a second and the memory is also very small. So that's absolutely feasible. On the other hand, we can also use local descriptors. So instead of having a single numerical vector that describes the whole image, we now have, very similar to what Alpha presented before, several local regions within the image, and now each of them has such a descriptor. So for example, 200 local features in each database image and 200 local features in the query image. So 200 numerical vectors for each database image, 200 numerical vectors for the query image. So now the comparison between one database image and one query images becomes the creation of a k times k similarity matrix. Exactly this combinatorial problem that Alpha also faced. So this is computational expensive to compute this similarity matrix, not for the single comparison, but for the 4 million comparisons that we have to do in order to compare all the database images to all the query images. So if we actually do this, we have about 160 billion descriptor comparisons, and this takes about 5 hours on my laptops and really consumes a lot of memory. So this is practically not a good idea to do on an actual robot. So now the idea is simply, okay, we observed the descriptors are high-dimensional vectors, so let's use HTC VSA to exploit the best from both worlds. To have the efficiency of the holistic descriptor and the expressive power of the local descriptors. How do we do this? It's a two-step approach. The first step is to encode basic information in high-dimensional vectors. And I've already showed you that we have those descriptors, which typically comes from neural networks. So these are learned high-dimensional vectors. And on the other hand, we have additional information. In case of the local descriptors, for example, their position within the image. And we can use engineering methods, just create some manual encoding of position to introduce this information and represent this information in the same vector space as the descriptors. And now the second step is to combine those vectors with the VSA operations. So we have bundling and binding, and we use two important properties of those operations. The first is that they can they can have as input several descriptors from the vector space, and the output is a single descriptor or a single vector from this vector space. So we can now combine several vectors into a single vector. And on the other hand, we can do this in a way that controls the similarity. And that's super important in this image retrieval task. So controlling similarity means for bundling, the output is similar to each input, and for binding, the output is non-similar to each input, but it's similarity preserved. So now I want to very briefly show the results from 2 papers where we adopted or applied this idea to this image retrieval task, together with my colleagues from Chemnitz, Kenny Schlegel, Stefan Schubert, and Peter Botzel. And you can look at the details for these approaches in these 2 papers, and we can talk about this later in the breakout rooms. So just a little bit of information about the general idea of those papers. So usually we have just a large set of image databases, large selection of data sets, and then run a series of experiments and compare our new approach to the state-of-the-art, the existing approaches, and create large tables with numbers. Okay, how do we apply this idea to those data sets? Okay, we have already seen we have those local features with the local descriptors. Now the goal is to create this holistic descriptor using VSAs to be able to have this fast comparison. And it's just these 2 steps. The first one is we represent everything as a high-dimensional descriptor for the output of the neural network that creates the local landmark descriptors. We just apply some pre-processing and already get our high-dimensional descriptors A, B, and C. And each of these local features has a position, and we use this manual encoding I showed you briefly before to create other vectors, PA, PB, and PC to encode the image position. And now we combine them with binding and bundling. This is a data structure that Kenny Schlegel will later talk about again, a bundled role filler pairs that just represents all the information in a single vector and can be computed very efficiently and turns out to represent a lot of the information in a single vector. It turns out this works really well for this kind of problem. So this is the big results table that I announced earlier. So here we can see that for a lot of data sets, we can calculate some number that just represents how well this approach performs. This is just a better illustration. So what we did, we evaluated some existing, basically deep learning based standard heuristic approaches and compared it with our new VSA approach. And it turns out that the average performance of our approach is considerably higher than the state of the art. On the other hand, we have to keep in mind that this is just an approximation of the exhaustive comparison of all the local features. So if we invest these 5 hours computing time, we can, of course, be better than the VSA approach. But the VSA approach is much more efficient. In particular, it's much more efficient and creates better results than other approaches that combine the local features in the holistic descriptor. Okay, just a brief outlook. What we can talk about in the breakout room is something we call vector semantic representations. So as a human, we can use a lot of semantic, symbolic information for localizations. For example, in Chemnitz, it's very easy to recognize this place because there is this statue of Karl Marx. And this is a very unique constellation of semantic entities to have this head in front of a building with vegetation and sidewalk under it. And we can also adopt this idea of representing the output of neural networks that encode some information from this scene together with additional information that we can engineer, like the layout of these semantic entities. We can combine all this information very similarly using VSA and HDZ tools in vectors that we can then use for this kind of localization task. And you're very welcome to talk to me in the breakout rooms about this approach. Thank you very much.
Thank you, Per, for presentation. All right, so we switch to the next speaker. And that would be Graham. Yes. Hello.
Okay. Hi.
Hi.
Can you see the screen?
Yes.
Okay, fine. Okay, so my name is Graham Bent. I actually run my own company called Neurosynapse Limited, but I've been working as a contractor with Cardiff University. And the work that I'm going to describe to you is work that we did under a joint UK-US research project sponsored by US DOD and the UK MOD. I'm just having a problem. There we go. So the challenge that we were looking at is that in future military operations, you're going to have lots of sensors working on edge of network communications networks, and you require multiple sensors and devices and services to dynamically configure themselves together on demand to perform new tasks. And you want to be able to do these at extremely low energies if possible. So that's the sort of scenario. And the idea that we had was, could we use hyperdimensional computing, VSA, to represent the sensors and services, and also the service workflow composition, the combination that you need to perform an application? Could we represent those as vectors, and somehow just by transmitting a single vector and exchanging it around the network, we could compose the application that we wanted dynamically? So that's what I'm going to talk about today. So in order to do that, we actually use a hierarchical HDC VSA binding scheme that uses a combination of role filler binding and cyclic shift binding. I'll not go into the details, but essentially you can build up any representation from a basic set of vectors at the bottom of the hierarchy and build up successively higher level descriptions of the vectors. And I'll show you an example of that as we go through. So the idea is that if a commander wants to be able to complete or construct a new task, which may be to discover a number of sensors and services and have them linked together to perform the task, the idea is that you can do that by describing the workflow that you want, but then the workflow is mapped automatically into a vector representation, and you simply inject that vector into your communications network. The devices themselves are self-describing, and they describe themselves as vectors. And the idea is that the sensors then compare themselves with the current request and offer themselves up if they match. And I'll show you how that works. So, for example, we might want to describe a number of vehicles or soldiers or whatever it might be, each with a different radio. And in this example, I'm going to show you how we would collect together or discover the services that we want and get them to all communicate on the same radio channel. So the idea is that each device describes itself in terms of its type, a vehicle or a soldier or whatever. It might have different roles and capabilities, but also it has a list of channels that it can operate on. And so we're going to do this in terms of a communications replanning, where we want them to switch between channels. But you can see that what we do is we build up from the lower level vectors, which are built up actually from vectors that just represent letters of the alphabet. So we describe words as bound vectors of just individual letters of the alphabet to create words into sentences and sentence descriptions. And we build up a complete description of the radio and all the associated parameters. And then we combine the radio vectors together into a communications or a workflow vector. So how does that work? Well, each radio describes itself. They're self-describing. So each radio can have a number of configurations, and it stores all the configurations that it can have within its own device. So in this particular case, this radio has 3 configurations. They're all the same parameters, but on the right-hand side, they could have different channels. So this particular radio can operate over channel 1 and channel 2, and in a slightly different configuration, only on channel 1, as an example. So what we're going to do is we're going to have a scenario where we have a current plan, and on the current plan, we have a number of assets operating on the different channels. So on channel 1, we have a couple of radios, a couple of vehicles. On channel 2 and channel 3, a different set. And the target plan is to move all these different assets around so that they're operating on the channels that we want them to operate on. So I'm going to, for simplicity, just represent these different assets in different colors with different colored dots. And so the map that I just showed you looks something like this. We have the current plan on the left and the target plan on the right. And the workflow vector, and I'm just doing it in a very simple way here so you get the idea of how it works, it is just a vector, a bundle vector of all of the different requirements that we want. So we want a yellow node on channel 1, another yellow node on channel 1, and so on. So 3 yellow nodes on channel 1 and a blue on channel 1, green on channel 2, and so on. So it's a very simple idea. But when you what you do is you inject the vector Z into the communications network, and you can see that when you do that, it multicasts the vector. So initially, the Z vector looks like YC1, so it's looking for yellow on channel 1. And if there is a yellow on channel 1, it compares its own description vector with the current state of the workflow vector, accepts the task, and so that now it receives the task. It now unbinds the vector and retransmits, and of course there's another yellow vector already on channel 1, so that accepts the task, and then it unbinds the vector and retransmits. In this case, there's not another yellow node on channel 1, and so what it does is it modifies the vector slightly. It jumps to channel 2 because it can operate on 2 channels, retransmits, but again, there's no vector on channel 2, and so it modifies the vector to say that I've already tried channel 1 and channel 2. Is there anyone who can operate on any of the other channels and retransmit this vector? And a red node offers itself up, drops down to channel 3, retransmits the Z vector, which discovers the node on channel, a yellow node that can move to channel 1. It hops back to where it was. This vector node takes over, retransmits the Z vector. You get the general idea, and hops around. And so if we just step through the environment, you can see that eventually we end up with everything on the achieved target plan. And just to sort of show how that works, we actually have represented this whole thing in a NATO scenario where we actually have a very low bandwidth network with a high fidelity representation in the simulator. So it represents the radios accurately. And we're operating on very low bandwidth, 17 kilobits per second communications tactical networks. And the idea is that we want to move or get these nodes to operate on different channels. So the channels here are shown as the different shading. And as we step through the scenario, what you'll see is that as the nodes transmit the vector, and as the nodes transmit the vector, nodes respond, take over the control of the vector, and then they retransmit it. So you'll see different nodes picking up the vector and then retransmitting it. And in the screen here, you can see which node responded, it switched, which channel it switched to, and the communications bandwidth that was consumed while we perform these different operations. And as we step through, you can see that gradually over time, the different nodes are moving to the correct channels. And then eventually we end up with actually 3 groups. The shading, for some reason, didn't appear at the end of the simulation here, but we've split them into 3 groups, now operating on the 3 communications channels. And we've got a record of the bandwidth that was required to do these operations. So you can think of this as what they call the battlefield, the Internet of Battlefield Things. You can think of this as the Internet of Things, so that's how the simulation works. Just to finish, this scenario and all the details were represented in a paper that we presented at SPIE in 2021, and in that paper we also showed, along with Geethan, who's going to speak in a little while, we showed how we could actually perform these operations with very low energies using a phase change memory device. And so all the details of that are in the 2021 paper. And then in 2022, we used a slightly different representation of the vectors. In the 21 paper, they were all 10 kilobit binary vectors. But in the 2022 paper, we used a sparse vector representation and showed that we could do the same thing using time to spike neural networks, neuromorphic processing. So that's the end of the presentation. And there's the acknowledgement to our sponsors. Thank you.
Thank you very much, Graham. I guess we continue with, let me see, Gitan. Gitan is here, right? Great to see you, Gitan.
Evgeny, yeah, I'm here.
Yes, so I think it's your turn now.
Okay. Yeah, so then let me share my screen.
It's half of it went into hyperdimensional space.
Wait. Okay.
Now.
Do you see it?
Yes.
Yep.
Okay. One moment, please. Wait, so I think I need to change the background I had for a previous event. Okay. So hello everyone. Yeah, so I'm Geetan Karunaratne from IBM Research Zurich. I hope you hear me well. Is that the case? Okay. Yeah, so today I want to show you some of the research that have been done at IBM Research Zurich, particularly in this field of VSA, vector symbolic architectures, with the help of my colleagues, Mikhail Hershey, Abu Sebastian, and Abbas Rahimi. Right. So to set the stage first, I would like to, yeah, I hope all of you have some basic background in the VSA. Is that the case? I hope.
Yeah.
Is that the case for the audience here?
Yes.
Yes.
Yeah. Okay. Good. Yeah. So this, yeah, on the left side, what you see is the traditional way of the way the VSA works. Here. What we have is a sequence of inputs that are represented in a low dimensional space, and then we go through what we call a pre-processing stage and then project it into high dimensional space. And then we do some kind of high dimensional vector manipulations through this encoder, where we get some composite high dimensional representations for different symbolic entities. And then we can do what we call backend operations, which are mostly like search operations, cleanup operations, and yeah, to do some kind of high-level cognitive tasks like reasoning and etc. Yeah, so then we can get the outcomes we want. So this is the traditional flow of how things work in VSA. What we notice in our research is that, particularly for certain type of inputs like highly unstructured and highly entangled type of inputs like images, this sort of encoding with the high dimensional VSA operations does not give us desired results. So this is why in our research we thought of remapping or replacing these front-end components with a more powerful like a representationally highly capable deep neural networks. And this is what you see on the right side. And still we try to make the training methodology such that the vectors that are spit out by this deep neural network are amenable to backend VSA operations, and then we do the final yeah, we do some backend operations to get the outcomes we want. So this is the basic idea. So to recap, what we have is on one side, on the front end, we have a deep neural network which can get arbitrary inputs. On another side, we have a backend VSA machinery, and we plug them together using a end-to-end trainable methodology. This was initially published in this work in Nature Communications called Robust High-Dimensional Memory Augmented Neural Networks. For those who are interested, can get a further idea on what we've disclosed here. taking this idea further, we were looking how we can make it work in a more general setting. So initially we looked at how few-shot learning can be done. So in 2022, we looked at how it can be further extended for class incremental learning with few shots. And here we also have some constraints, which you'll see soon. And this code, we also made it publicly available on the IBM GitHub page. So those who are interested can take a look. Yeah, so the idea of a few-shot class incremental learning is you get a few examples from a certain class. Like we're working through sessions. In one session, we will get some training examples from certain set of classes with which we can fill up what we call an explicit memory. We use some kind of a architecturally wise a standard ResNet plugged into some retrainable fully connected layer, and then we have our own training methodology as explained in this paper, which we use to train it end to end. But the idea is that once you finish one session, we can move on to further sessions with the new classes coming in, which we accommodate through this our architecture by having an explicit memory which can be evolved, which can be extended into have further representation stored on the explicit memory. Yeah, so we have constrained our explicit memory to work with the minimal memory requirement, that is having just one entry per class represented inside the explicit memory. Okay. Any questions up to here?
Not as I see in the chat.
Okay, good. So now, so in the paper, you will see that there are several modes of operation that we discuss. But for this today's demo presentation, we choose one mode, which is in the paper we call it mode 1. The reason is it's the simplest of all the modes that we presented. At the same time, it achieves slightly lower accuracy, still at the state-of-the-art level accuracy. So what does this mode 1 do? So simply put, this mode 1 will take these examples from a given session. So these are the we call it a support set. A few of examples. In this case, you can see 2 dog example and 1 cat example. We send it through the feature extractor and the fully connected layer, and then what we store inside the explicit memory is the average of the different embeddings that we get per class. So in this case, the cat example will get a high dimensional vector and at the end of fully connected layer, it will be stored as it is. The dog example, there are 2 of them. These will be averaged before being stored in the explicit memory. So yeah, so what I have not shown here is what exact methodology we use here. It takes a bit more time to explain, but for those who are interested, can you follow the paper? It's basically based on the meta learning approach. Yeah, so with I think you most of you know that the high dimensional vector computing, high dimensional computing, or the vector symbolic architecture is based on the fundamental of this blessing of the dimensionality. So with the high dimensional representations that we have here, we are able to have a training methodology which will make sure that the different classes get quasi-orthogonal representations in the explicit memory, which allows us to later on do these classifications at a higher accuracy, right? So so what we do next, so let's say we have a new session with a new class coming in. We keep the previous representation as it is, and then we directly feed forward the new example through the pre-trained these modules to get the high dimensional vector representation for the new class, and then just add it into the explicit memory. So there's no retraining involved in method 1, which makes it the fastest way to inference, and also make it the least computationally complex mode of the 3. In this slide, you see the performance of our method mode 1, which I just described in the previous slide, versus another mode which we call the mode 3, where we do some kind of retraining on the fully connected layer and allows us to get a further accuracy boost. But compared to the previous 2 works that appeared in 2021 CPR and EURIS 2017, we are performing, having a better accuracy. So this was done, this evaluation was done on OmniCloud dataset involving 423 novel classes, and we do this meta training on the 1200 base classes. Yeah, we did further evaluations on the CIFAR 100 and mini ImageNet datasets, and today I will just show a demo on how this this works with the CIFAR 100 dataset. So yeah, so far what we have presented is the algorithmic advancements, what we do with the VSA mode of computing. And now here, what you're showing in this slide is how this concept of evolving explicit memory can be implemented on in-memory compute crossbar. So I think in the previous presentation, Graham briefly mentioned the work that we done in 2020, which is about having an in-memory computer being able to do the basic operations of high dimensional computing. So we are taking this one step further by introducing novel programming scheme for the cross points of the crossbar array using this method called physical superposition. So if you remember in the previous couple of slides earlier, I showed you how we do the accumulation of the two examples or more examples from the same class. We do the averaging. So this average operation in this particular, the second or the third paper now presenting in this this talk is appeared in ESTER, and here we are doing a in-memory realization of this few-shot learning, few-shot continual learning using a dynamically evolving explicit memory. And the idea is simple. So you take a crossbar array, and each of these can be programmed. What we do specifically novel here is that we try to program the devices in such a way that it carries the average value of different examples. For example, starting from a dog, one of the dog examples, we will have our a device that's on a cross point into a certain conductance, which is on the lower end of the conductance spectrum. And when we get a new example, we will program the same device to a slightly higher conductive state by applying what we call a partial set pulse. And what it achieves to us is that it will make this vector represented on the crossbar as the average of the two examples that were presented to these in-memory crossbar array. So yeah, we can continue further. We can have further and further examples sent through this feature extraction and the fully connected layer, and then the resulting high dimensional vector we can program with the partial crystallization pulses, so that it's the conductance of the device gradually shifts towards a higher conductance ranges, so that the average operation we perform on in memory without using explicit arithmetic units. Any questions so far?
No,
Okay.
I think it's fine.
Okay. Yeah. So this graph here just shows the evolution of conductance when we apply different partial crystallization set pulses. Initially, the conductance of a device will stay at the lower end, and while we apply a crystallization pulse of this shape here, we are going to get a gradual increase on the conductance of the devices. As we go further and further, the marginal improvement in the conductance is lower. So that means we have a certain range that works well to give us the required performance. So in this work, we are looking at applying up to 5 examples in this range here to still get the accuracies in the range of the software, that the accuracies that I presented earlier. Right, so I think with this, we can move on to the demo. Yes.
Gitan,
One moment. Yes.
I think we can. I mean, how long is the demo? Do you want to show it?
About 2 minutes.
Okay, let's go for it. Yes. Let's go for it.
Yes. Okay, good. Oh, wait. Wait. How do I pay it? With the pointer, I'm not able to click on the play button. Anybody know how to change it? Or I can quickly go back and then.
You should share audio somehow.
Oh, you cannot hear?
You, yes, but not you on demo.
I see. Okay. Now I have to choose. Is it a Zoom setting?
Yeah, in view options.
Yeah, it's a Zoom setting.
Okay.
Yeah,
In the share, I guess, right? If I go to share, then yeah, share the sound. Okay, got it. Okay, let's try again. Sorry for the. Hello. In this demo, I'm going to show you.
That's great.
Show you for the first time how few-shot continual learning can be done on an in-memory compute chip. This chip was developed at IBM Research Zurich Lab. We are using images from CIFAR 100 dataset. First thing we do is we select classes. We are using animal classes. For example, we can choose elephant as our first class. And what we do next is we are going to feed a few training examples from the elephant class one by one through a neural network. The neural network is pre-trained and meta-trained. The result of the neural network is a high-dimensional vector representation, and we are sending these vectors one by one to this in-memory compute chip. Inside the chip, it will select one of the rows on the array, and then they get programmed using partial crystallization set passes. Then we select the second class, which can be something like wolf. Similarly, wolf images are fed through the same neural network and the array is programmed. You can see how the conductance of the devices on the selected rows varies to represent the vector updates. At this moment, we can query our learner from query examples from, let's say, wolf class, and we can see that it gets 100% accuracy. When a query image is given, similar to the training images, they will be converted to a high-dimensional vector and applied as voltage pulses on one side of the in-memory compute array. The resulting similarity vector is received on the other side. However, if we evaluate the learner on images from a different class, for example, like leopard class, having seen no images from this class so far, the learner will misclassify it as either elephant or wolf. To enable continual learning capability, we just need to feed in a few training images from the leopard class. Once a row on the in-memory compute array is programmed to represent the leopard class, we are able to successfully classify the leopard query images. We are very excited. All right. So I will try to quickly recap what we so far discussed. So VSA, we know is a good in certain things with the robustness, memory-centric approach to computing and being energy efficient, which is reason why we were able to show it, demonstrate it on these in-memory crossbar arrays in the first place. But there are certain drawbacks, like being not able to be able to represent unstructured inputs and which are highly entangled. So for this, we make use of DNNs at the front end to guide. So we guide with our training methodology to for the DNNs to emit quasi-orthogonal embeddings for different classes. This allows us to now do new applications like few-shot learning and continual learning, which further takes the field towards more general AI or general artificial intelligence. And we can also see how this approach can be used for further cognitive tasks like reasoning and etc. And yeah, here we are relying on a backend VSA that can perform more complex operations and tasks. Right. With that, I would like to wrap up my talk, and thanks you everyone for your attention. If you have further questions or any questions, yeah, I'm happy to take them.
Yes, and thank you very much, Gitan. Thank you indeed.
Sure.
Yes, applause from here and the online audience. Questions we take in the breakout rooms. So if you wait for the last talk, there is a breakout room with your name.
All right.
So
Yeah.
you can go there and see if some people will join.
Sounds good.
Okay, so Kenny.
Yeah, hello to everyone. Let me share the screen. I hope my slides are visible.
Yes.
Yeah, okay, great. Yeah, hello. I'm Kenny and I'm a PhD student from the Chemnitz University of Technology, and I would like to talk about the hyperdimensional computing in time series classification, where we used simple HDC operations to extend an existing state-of-the-art method to to get better accuracies in some cases or in some data. First, let me show you a bigger picture. A common structure in time series classification is as follows. So we have as input our time series. For example, it can be data from autonomous sensors, from a robot or autonomous car, or the signals can be Maya signals or from audio or something else. Then usually the data goes into an encoding mechanism, so to extract some features, for example, with convolutions or dictionary-based approaches, or with shapelet-based or model-based approaches. And based on these data encodings, we can use a classifier to classify our input. And these classifiers can be based on regression or on artificial neural networks or nearest neighbor search or something else. And now we incorporate hyperdimensional computing in this data encoding step. So we use hyperdimensional computing to systematic incorporation of model knowledge in this data encoding step. And in our application, we used a state-of-the-art method called Mini Rocket, because it is one of the best performing method in terms of performance and accuracy. And there we extend this state-of-the-art method by HDC to incorporate global time encoding. So we incorporate additional information within the state-of-the-art method. And the result is that we have mini rockets, so a state-of-the-art algorithm with additional information about the same computational effort. So it's a more general version of mini rocket, which incorporates additional information. To show a concrete example where it can be beneficial to incorporate this HDC in this mini rocket approach, can you see here on a synthetic experiment? So imagine we have a signal within a predefined time period, for example, a day, a week, or a month. So there are two classes. Class 1 is we have a peak in the first half of the signal, and we have class 2 with a peak in the second half of the signal, and we have some additional noise. And to distinguish between two classes, it is important to look at the temporal order of the peak. So is it the first or the second half? And if we apply the mini rocket approach here, then we only reach an accuracy of 67%, by the way random guess is around 50%, so we have the same amount of samples from class 1 and class 2. And if we incorporate HDC in this mini rocket, we can increase the accuracy up to 94%. And yeah, the question is, why is incorporating HTC in mini rocket a good idea? And to answer this question and to see where we use these HTC mechanisms, we have to clarify or answer the question, how does mini rocket work? So mini rocket uses as input a time series, so a signal over time, and then it uses random filters, so for random convolutions. There are many convolutions with different dilations and so on. So we got several responses over for each time step from each random convolutional filter. So as you can see here, we have over time different feature vectors, and in that case, these feature vectors are high dimension vectors around about 10,000 dimensions. And mini rocket, in mini rocket, these features are accumulated over time. So just compute a sum for each response over time and got an overall feature embedding vector. And this feature embedding vector can be used for classification. In that case, it's a simple rich regression. And the problem here is, or it can be a problem in some data, if we just sum up over time, because accumulation over time loses the information about the location in time. So we do not know when a specific feature appears in time, since we just accumulate over time. Hence, it would be better to encode a global time context before we accumulate over time. And here comes HTC into play. So now we want to add this temporal information to mini rocket. And as I said, we have feature vectors for each time step, and these vectors are still in a high dimensional fashion. And now we can use these high dimensional vectors for each time step and associate each feature vector with its temporal position by using the HTC operation binding and bind the feature vector to a timestamp vector. And then using the bundle operation, which is equivalent to sum over time, to overlay all the pairs of feature timestamps. And this mechanism is also called the bundled role filler pairs, because we bundle a set of pairs that consists of features and timestamps. And for creating these timestamps, we also introduce a parameter S, which influences the similarity of timestamps. So in other words, how much should be the temporal context into the encoding? Or let's say, we are using HTC operations for creating these timestamps based on the scaling parameter S, and the parameter S decides whether and how strongly the global time is encoded into time series. So we can, with this parameter S, we can enable the global time encoding and adjust the strongness and the strength of the global time encoding itself. And on the next slide, I would like to demonstrate why it is important to choose the correct hyperparameter S, so decide if global time encoding is beneficial or not. Because here is a figure where we plot the change in accuracy in a real-world benchmark data set. So here you have the different data sets, and here different parameter S. And we plotted the change in accuracy. And you see blue means the accuracy increase, and red means the accuracy decrease compared to the original mini rocket. And if we have a scaling parameter S equal to 0, there's no temporal context. So this case is equivalent to the original mini rocket. And if we increase the parameter s up to, for example, 6, there we have a high temporal context. So yeah, and so just as an explanation of the figure itself. And as you can see, for some data sets, it is beneficial to incorporate temporal context, as you can see here on this line, because if we increase the temporal context step by step, the accuracy is getting better. But there are also some data sets which are not benefits from the temporal context or the global time context encoding. As you can see here, if we increase the parameter s, some data sets are getting worse. So that's why it is very important to know if global time encoding can help. And in our, now we have seen the core idea of incorporating HDC in the mini rocket. At the beginning of the talk, I showed a synthetic example where it's really beneficial. And as I showed you on the last slide, we have also we did also experiments on real world data, and to see another figure where we demonstrate the improvements on real world data, I would like to show this bar graph. It's just a plot of the same real world benchmark data set ensemble. And as you can see, if we find the correct S, so deciding correctly if incorporating global time is beneficial or not, then you can see for some data sets we are getting improvements. There are many data sets which are not getting better if we incorporate global time context, but here, for example, this data set can be benefit from incorporating global time context, and we can improve up to 12%. Okay, just a short summary. We have seen that a simple HDC mechanism can be used to extend a state-of-the-art approach in the time series classification domain. And this can improve the accuracy for univariate time series by just adding these simple mechanism of bundled row filler pairs. In the synthetic experiment, we have seen that prevents failure in corner cases. So the temporal order is very important to classify different cases. And it is about the same runtime as the original mini rocket, since we are already in the high dimensional space within the mini rocket method itself. More details can be found in the recent paper from the IGCNN conference. The paper and the work was together with my colleagues Per Neubert and Peter Protzel. And there's also ongoing work on this approach, for example, to extend it to multivariate domain and make this approach somehow better. That's it from my side, and thank you for your attention.
Thank you, Kenny. All right, I think we listened to all the talks of invited speakers. So now what happens is that we have some time left in the agenda for interaction. So I therefore ask all people online to join one of the breakout rooms. And we have joined already. So let's have some interaction. And in this main room, I want to thank you all for participating.